total record. Okay. Yeah, so in the previous, so we finished in the last time on the combinatorial identities. I will remind you what we are talking about. Okay. So,
sir, I have a question. Are those lectures recorded so we can look at them later?
yeah, I just started the recording, so you.
Thank you very much, sir. Thank you very much.
Yeah, okay. So we're talking about some identities, and we proved the following one. So we proved that n choose k is equal to n choose a minus k. We proved that n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. Also, we prove the binomial theorem. So if you want to expand the a plus b in the to the nth power, it's a to the nth power plus n choose 1, a in the n minus 1, b1, etc. And using this, we prove that the sum of the binomial coefficients will be 2 to the power n. And also we talk a little bit about Pascal triangle. So if you write the triangle of ones and then put the sum of two numbers between them, then we will have the triangle consisting of binomial coefficients. So we will have the full triangle of binomial coefficients and so on. Okay, so we will continue with the following identities. First of all, we want to find the signed sum of the binomial coefficients. So for example, we're not taking the sum, but of the alternating sum. So we have the n choose 0 minus n choose 1 plus etc. plus n choose n times minus 1 into the nth power. Can somebody answer what will be the sum?
Only the 0? Is it 0, sir?
For all n.
Sorry?
For all possible n.
Yeah, I said that.
For each n, it will be 0, yeah?
Yeah.
Okay, and how do you prove it?
I think all the terms will cancel out. By the first combinatorics identity which you wrote.
Okay, let's look at the first identity and look at, so can we use it or not? So if n is odd, for example 5, then if you look closely, you will see that, as you said, all terms will be cancelled because we see that, for example, 5 choose 0 is equal to 5 choose 5 using this first identity, so they will be cancelled. 5 choose 1 is equal to 5 choose 4, and 5 choose 2 equal to 5 choose 3, so the answer will be 0. But if you take, for example, 6, n equal to 6. Then you will see that this identity doesn't give us the cancellation, because 6 choose 0 is equal to 6 choose 6, and then we can't cancel them because they are the same. They have the same sign. And so, how can we prove that this is 0 in the when n is even?
Sir, if I was thinking we can use the binomial theorem, substitute a equals 1 and b equals -1.
Yeah, of course. So the easiest proof is the following: you just take a equal to a equal to 1 and b equal to -1, and just expand the brackets. And if you see this formula, so we just see that it will be n choose 0 minus n choose 1. So it will be plus 1 times -1 plus n choose 2 times -1 squared, and so on, plus n choose n times -1 in the nth power. So we can rewrite this as the alternating sum. And of course, it will equal to 0. It will be equal to 0. So this is a little mistake here, because if we take n equal to 0, then 1 minus 1 in the 0th power will be just, so by the definition it will be 1. So if you take here n equal to 1, you will see that we have only 0 to 0, and it is equal to 1. So the full answer will be the following. It will be 1 if n equal to 0, and 0 is n if n is greater than 0. Yeah, okay.
Yes, sir.
Yeah, okay. And also we can prove it just if we look closely at the Pascal triangle. We also can prove it using the Pascal triangle. I will show it. So so remember that we prove the identity with the 2 power n using this Pascal triangle. And his idea is that here we have the same idea. So each number occurs in the following row 2 times. So for example, we can rewrite this fourth row like 1, 1 plus 2, 2 plus 1, and 1 plus 1. And we see that each number occurs exactly 2 times in the next row. Oh, sorry, this is we haven't here. Yeah. And so if we look at the alternating sum, so we have minus here, then each number occurs in the next row, 1 time with sign plus and 1 time with sign minus. So they cancelled, and so we have the sum equal to 0. So if we rewrite, we can also prove it not using the Pascal triangle. Just write that n choose 0 is equal to n minus 1 choose 0, and n choose 1 is n minus 1 choose 1 plus n minus 1 choose 0, and so on. And if we use the use this identities and put it in this equation, you will see that all terms will be cancelled, and so we will also have 0 as the answer. Okay. The following identity will be just the sum of the squares of binomial coefficients. So we also will know the sum of the coefficients, and can we find the sum of the squared of these binomial coefficients? And maybe I will give you the answer, and we will prove it. So I want to prove. I want you to prove that this sum is equal to n choose over n. Okay, does someone have any idea how to do that?
So I tried using the first identity that shows
Yeah. Yeah. Okay.
that it's symmetrical.
Yeah.
So I ended up at this answer will be equals to 2 times the binomial theorem of times the summation of n choose I from I equals 0 to I equals n over 2. Okay, I'm not sure, sir.
So of course, if you use the symmetry identity, you can write this as like something like that. So you just write each square as the product of the symmetry binomial coefficients. But how to calculate this one? So I don't understand how do you calculate this using the binomial theorem.
I didn't calculate it. I was trying to. I wasn't sure
Okay,
if
okay,
it's gonna work.
okay. So you maybe you can think of how to describe the binomial coefficients of 2n over n. So 2n choose n. So we have like 2n elements. elements, and we want to choose n elements from this to n. How can we describe the possible variations of choosing the n elements from to n?
So I choose n.
So in the right hand side we have to n choose n. So we need to just look at the combinations of choosing n elements from to n elements. And how can we describe this? Using the choosing of something from n elements.
Oh.
So do you need a hint?
Sir, could you give me 2 more minutes? Then
Yeah,
if I can't find it.
2 minutes, yeah. Okay, so if anyone has any questions, you can ask me. So if you don't understand what I said before earlier.
Sir, I think you should go ahead and show us the proof, sir.
Okay, so again, we can give different proofs of doing this, but the simplest one I think the following. So you just look at so you need to choose n elements from to n elements, and we need to describe it in terms of choosing something from n elements. So how can we choose from n elements? We can just divide to n elements, but by two parts. Each of one contains exactly n elements. And then what do we need? We need to choose k elements from the first part and n minus k elements from the second part. And k differs from 0 to n. So if we choose, for example, 0 elements from here and elements from here, it will be exactly the following number of possible variants. So it will be n to 0 from the first part and n to the second part. If we choose one element from the first part and n minus one element from the second part, it will correspond to this guy. So we just took n choose 1. It's a number of possible choices of one element from n, and here we can need to choose additional n minus one elements, and so it will be the binomial coefficients of n over n minus one, and so on. So each possible combination can be described as we choose some elements from the first part and some elements from the second part, and so we will describe each possible combination in terms of a product of two binomial coefficients. And again, we can use the binomial theorem here, because what is the 2n over n? This is the coefficients in 1 plus x in the 2n's power. It will be coefficients before x in the n's power. So here we have c to n over 2n choose n. And we also can describe 1 plus x in the 2n's power just as the product 1 plus x in the n's power times 1 plus x in the n's power. And if we want to calculate the coefficients before x in the n's power, we just need to choose we just choose the x in the k's power from the first bracket and x in the n minus k power from the second bracket. And if you want to choose x in the k power, there will be a coefficient cnk, and the next one will be cnn minus k. So here we will have the product of these coefficients. And so if you want to obtain x in the nth power in the right hand side, we need to choose x in the k power where k differ from it will be 0, 1, etc. n, and x in the n minus k power from the second bracket, and so we will have the sum of the product of these coefficients. So we'll have cn0 times cnn plus cn1 times cnn minus 1, and so on until we have cnn cn0, and it will be equal to c to nn. Do you understand? Maybe have questions?
No, it's pretty understandable, sir. That's
Yeah.
pretty good.
Okay.
Thank you, sir.
Okay. So this next one will be helpful to if we one of the useful formulas. So what if we want to find the sum of the powers of the first n natural numbers? So we want to find the number of numbers from 1 to n, the sum of the squares, the sum of the cubes, and so on. So we start with the first one. I think you already know this formula. You know that sum from 1 to n is just equal to n times n plus 1 over 2. Yeah, is it correct?
Yes, sir.
Yeah, I think it is correct. Yeah, okay. So how, using the formula, we want to, for example, how to find the formula of the sum of the squares. we can rewrite. So I want to rewrite the sum of the squares in terms of sum of some kind of binomial coefficients. Then find the identities that I need to prove, and then it will help me to find the formula for the sum of squares, and I can also find, if I know the sum of the squares, that I can find the number of sum of the cubes, and so on. So how can where can I find the sum of the squares? Let's look at the binomial coefficients with where we have the something over 2. So we know that if we take ck2, it will be equal to k factorial over 2 factorial times k minus 2 factorial. So it will be equal to k minus 1 over 2. And we can rewrite this as k squared minus k over 2. So if I want to calculate the sum of the squares, I can do the following. I can just write the 2 over 2, 3 over 2, 4 over 2, and so on, n over 2, and it will be equal to 2 squared minus 2 divided by 2 plus 3 squared minus 3 divided by 2, and so on, until the n squared minus n divided by 2. I'm just using the previous formula. Then I can just write this as, so I can also add here the 1 squared minus 1 divided by 2 because it's equal to 0. And so I can write this as 1 squared plus 2 squared plus n squared, all this divided by 2, minus the half of the 1 plus 2 plus 3 plus etc. plus n. And this is I know because I know the previous formula. So here we'll have the n times n plus 1 over 2. So if I write this, so if we want to find the sum of the squares, all I need to do is just to calculate this sum of the binomial coefficients. And just add the n plus 1 over 2. Yeah, is correct. So all I need to do so if I want to find the sum of the squares, all I need to do is just find the sum of binomial coefficients. Okay, so what you need to do is to find the sum of the Okay, so I want to give you just maybe a couple of 3 minutes, and you can just try to find the answer by yourself, and then we will discuss. So also it is helpful just to look, maybe I make a little hint. So if we look at the Pascal triangle, then we can see that where are these numbers. So for example, theta over 2 is here, 3 choose 2 is here, 4 choose 2. So all we need to do is just calculate this part of the diagonal. So this sum is just the sum of coefficients of the diagonal. And also, if we look at the first identity, we can also look at this as the sum of the diagonal, but the previous diagonal. So this is just exactly the number of the elements in the previous diagonal. So it's just like the sum of the 1 choose 1 plus 2 choose 1 plus etc. plus n choose 1. So we see that the sum of the diagonal in the Pascal triangle can help us to find the sum of the sum powers. So sum of the cubes, sum of the squares, and so on.
Well,
Yeah.
sir, with that hint you gave us, n choose 1 is the same as n, so that means it's the sum of from 1 to n.
Yeah, of course we can. So you want to rewrite this as the sum of the as a diagonal or something else? I just don't understand. So of course we can use the symmetry rule, and then we can rewrite this. For example, we can choose not this diagonal, but so we can choose the green instead of green. We can look at this diagonal, but I think the answer will be the same. So it doesn't matter what diagonal we choose. The logic of the answer will be the same. Okay, so maybe someone has any ideas? Maybe the answer? Yeah.
So let me try. So I was thinking n into brackets n plus 1 over 2 plus n into brackets n minus 1 over 2.
Yeah, but I can't give so I want to give the answer just in terms of binomial coefficients. So this is a formula I can get. So I can get like for arbitrary k, I can find the sum of the binomial coefficients in part of the Pascal triangles. So in terms of
So I think it's n squared.
n squared here for the sum n squared.
Yes.
But if n equal to 2, then the answer is 2, so it is not squared. It is not n squared. So, for example, I can look at the every part of the diagonal here.
Wait, so the diagonal we're talking about for n choose 2 is the one in green, right?
Yes. So we just want to calculate the sum of the green elements. And we can.
Yeah, so I think it's n squared then.
Yeah, but
Or not. Yes, maybe.
Okay. Sorry. I miscalculated here. Yeah, of course, the first sum is 1, but then will be 4, then 10, then 12. And also from this, you can get the answer. So it will be 1, 4, 10, 12, and 35. And I think it will help you to find the answer. You will see that this is exactly the following diagonal. Then the elements in the following diagonal of the Pascal triangle. So the sum of the first element is this element. The sum of these two elements is this element, and so on. And it is easy to prove it because so if you want to calculate the sum, you just look at this trick. So you will write this number here because it is equal to 1. And you see that sum of these two elements, 3 and 1, is equal to 4. Sum of these two elements is here, and sum of these two elements is here. So the answer will be this element. So the answer will be here is Cn plus 1 over 3. And the proof is the following. So if I want to calculate the sum, I just rewrite 2 choose 2 as 3 choose 3. And then this sum is by our identity is equal to C for 3 plus C for 2, it will be equal to 5 over 3 plus C5 over 2, it will be equal to 6 over 3, and so on. And so just using this trick that I explained at the Pascal triangle. And so if you calculate the sum, it will be nothing but C n plus 1 over 3. 3 n plus 1 by 3. Do you understand? Do I need to repeat it? Is it clear?
Yes, sir. You don't have to repeat it. Thank you very much.
Okay.
So wait a second.
Yeah.
So what about n squared minus n plus 1? I think, oh, damn it.
Again, n squared minus n plus 1.
Yes.
Okay. So the answer is 1, 4, 10, 20. So if you take n equal to 2, it will be
Damn.
4 minus 2 plus 1, it will be 3, but the answer is 4.
Ah.
So the so let me write this identity. So the sum of the squares will be equal to 2 times n plus 1 to 3 plus n times n plus 1 over 2. And so we can write this equal to 2 over n plus 1 times n minus 1 over 6 plus n times n plus 1 over 2. We can move out the n plus 1. And we have here n minus 1 over 3 plus 1 over 2. And if we calculate this, it will be n times n plus 1 divided by 6. And here we will have 2 times n minus 1 plus 3. And it will be 2n plus 1. So we have the following formula. The sum of the squares will be n times n plus 1 times 2n plus 1 over 6. So we just can check it. For example, if you have n equal to 3, we'll have sum of the first 3 squares, which will be 1 plus 4 plus 9, 14. And here we'll have 3 times 4 times 7 over 6. And we will have the same answer. So for example, for n equal to 3, it's true. So I think we checked that we didn't miscalculate it. Okay, any questions?
No, sir.
Yeah, okay. So what about if you want to calculate the sum of the cubes? We can use the same technique. So where we can find the cubes? We want to calculate the number of binomial coefficients with the base 3. So here we have 3 times 2 times 1 plus 4 times 3 times 2 over 6 plus etc. plus n times n minus 1 times n minus 2 over 6. Okay, so how can we rewrite this? So n times n minus 1 times n minus 2 over 6, it will be n cubed minus 3n squared plus 2n over 6. So we have sum of the cubes over 6 minus 3 of sum of the squares starting from 3 over 6 and plus 2 with the sum of the ones over 6. And of course we can add the 2 and the 1 because here we'll have 2 times 1 times 0 and 1 times 0 times minus 1 over 6. And so we can just rewrite this using so we can imagine that we summarize it from the 1, not from the 3. And we already have the formulas for this guy and this guy. So we want to find this sum of the binomial coefficients over 3. And then we can find the sum of the cubes. So the answer will be that sum of the cubes is just 6 times the sum of the binomial coefficients over 3 plus 3 of squares minus 2 of the ones. So the formula for the squares is n times n plus 1 times 2n plus 1 over 6. This formula is n times n plus 1 over 2. So all we need to do is find the number of coefficients with base 3. And the idea is the same as the previous idea. So for example, so I will write this diagonal again here. And here we have the diagonal like 1, 4, 10, 20, 35. So if we want to calculate the sum of it, I just, again, I rewrite this one, move to here, and then the sum of these two guys will be 5, these two guys will be 15, then 35, and so on. So the answer will be 7, so n plus 1 over 4. Again, we can prove it, just change 3 over 3 as 4 by 4, and then using the combinatorial identity, which is just using the rule, the sum of the binomial coefficients. And so we can just, it is equal to n plus 1 times n minus 1 times n minus 2 over 24. So we can find the sum of the cubes, just 1 over 4 times this product plus 1 over 2 times n plus 1 to n plus 1 and minus n times n plus 1. Of course, we can move out the n plus 1, and here we will have of maybe over 4. And you will have n minus 1 and minus 2 plus 2 of 2n plus 1 minus 2. And so we can just calculate it. So it will be so I need to check if I didn't. Okay, so here we have minus 4. Yeah. So it will be cancelled, and all we left is n squared plus n, which is just n plus 1. Okay, so we have n plus 1 over 2 squared, and this is the true answer. So we just find the sum of the cubes, and moving on, we can find the sum of the 4th power, 5th power, and so on. So this is the technique. We didn't have the explicit formula for arbitrary n, for arbitrary k. So we didn't have the explicit formula for the sum of the k powers. But we have an algorithm which we can find the using the iteration. If we know the formulas for the first sum of the k powers, we can find the sum of the k plus 1 powers of the first n natural numbers. Okay. Okay. So do you have any questions? Maybe I will. I'll talk a little fast. Okay. So do we need a break, or I can just continue the lecture?
You can continue, sir.
Okay. Okay. So the we're talking about binomial theorem, and I want to talk a little bit about the generation of the theorem of the when we have not 2 parameters but more parameters. So I will talk about polynomial coefficient and polynomial theorem here. So suppose we have not, so when we talk about the combinations, we just look at the set of the n elements and just then took the k elements from them. So we just we can describe it as we just have two colors, for example, blue and red, and then just colored some elements in blue and the other elements are colored in red. So we just divide them into two separate groups. I want to ask a question: what about if we need to divide them in more? If the groups not just two of them, but there are many of them. So, for example, we want to divide n object of the n element set into k different types of objects. So, suppose we have an element set, and we just give the type of object. So we want to have n1 elements of type 1 and 2 elements of type 2 and so on, and k elements of type k. And we suppose that sum of this n1, etc., and k is equal to n. So we divide n into separate kind of objects. So how many possible ways can we do it? So, for example, we want to. It is useful, for example, if you like consider the some word, for example. For example, Mathematica, and then we just want to calculate the number of different arrangements of the this word. So we rearrange the letters, and we want to find the possible how much words can we get from this one if we just rearrange the letters. And here we have. So if all the letters are distinct, then we just have the formula for the permutation. It could be n factorial. But here, some of the letters coincide. So, for example, we have 3 A's, 2 T's, 2 M's, and so we need to have more accurate formula. And this is just the idea of polynomial coefficients, because here we have 2 objects of type M, 3 objects of type A, 2 objects of type T, and all other letters have only 1 object. And we want to calculate how many possible permutations we will have. So how many arrangements do we have from this word? Do you know how to calculate this answer? So how many different words? By word, I just said just the sequence of the letters. We can make from this one. Or you can imagine that we have, for example, some colors. So we have an element set, we have colors, and we want to rearrange this. So this types is just the colors of the elements. So we fix the number of the colors of elements of such color, and then want to calculate how many arrangements do we have. So can someone give me? Yeah.
Sir, maybe n factorial over size of the set of type 1 times all the way to size of the set of type n.
Yeah, so the answer will be just like, so here we'll, for example, we have 11 letters. If I didn't miscalculate it. Yeah, and so we need to divide it. So if you rearrange, we can, so the idea is the following. We can assume that all the letters are distinct. Then we have 11 factorials. And then we just calculate all the identities between the words. So if we look at these two letters, then we can put them so there are two types of arrangements of these letters. So we can put the first one in the first place and the second one in the second place, and the second one in the first place and the first one in the second place. So we just need to divide it over 2 factorial. And for the a's it will be 3 factorial, and for the t's it will be 2 factorial, and the others are just 1 factorial. So this polynomial coefficients is denoted by p of n1, n2, etc., nk, and it's just equal to n factorial over n1 factorial, n2 factorial, and nk factorial. So this is just like a proposition, and the proof is I just describe it. I just tell this is
Yes, sir.
in simple way. But if you just to prove it more accurately, then you just take. So you just first need to choose n1 elements of type 1. We need to choose n1 elements of type 1, and there's exactly n choose over n possible ways to do that. So if we choose n1 elements, then there is n1 elements left, and we need to choose n1 n2 elements of type 2 from these elements. So the number of possible variations will be n minus 1 over n2. And then we choose the elements of type 3 from the n minus n-1, n minus 2, and so on. So the final formula will be like that. So first we choose n1 elements from n element set, then we choose n2 elements from n minus 1 element set, then we choose n3 from n minus 1, n minus 2 element set, and so on.
Sorry, sir.
Yeah.
I'm not really understanding this proof, sir.
Yeah,
So
okay.
please start again.
Yeah, okay. So we want to divide the n elements into this type of objects. So first of all, we need to choose which elements will be of type 1. We'll have exactly n1 elements of type 1. And if you want to choose, so again, we have n element set, and we want to choose the n1 elements. This will be the type 1. And the number of possible ways of doing that is just the binomial coefficients n choose n1. So we just choose any n1 element subset of n element set. And if we choose them, then we need to choose the n2 elements from the other elements. So we need to choose n2 elements from these elements that are left. So this will be from the n minus 1 element. So we have to choose n1 element. We have n minus 1 elements left, and we need to choose from them n2 elements. And this will be n minus 1 choose n2. And so on. So each time we just forget about these elements that we already chosen elements, and then we will count that elements that are left, and then we choose the next elements from this one.
So why are we choosing? Is it to fill the spaces?
So we need to take the elements. So we need to find what elements can be the type 2 elements, and so for we can consider these elements of types as we just choose. First we choose elements of type 1, then we choose elements of type 2, and so on. And so we just describe this separation just as the iterative procedure of choosing the elements. If I understand the question correct? No?
Yes, sir. So if we say n choose n1, we're just that's the number of subsets of size n1.
Yeah,
right?
we just determine which elements is of type 1. Yeah. So we just choose the elements of type 1. Because,
Okay.
for example, if you take about the word Mathematica, we just need to choose the two positions where we can put the element m, and we can choose the two positions from 11, just like C 11 choose 2. Yeah. So we just choose the two elements where we can put m. Then we choose the three elements from the ninth elements from the left. We can put the letter A. Then we have 6 positions left, and we choose the two elements where we can put the letter T, and so on. Okay?
Okay, sir.
Okay. So, and the last one will be, so if the nk element left, we can just it's like, so, and the last one will be equal to 1 because we have nk element left, and we can just choose them one ways because we need to use all these elements. And so if we rewrite the formula using the formula for the binomial coefficients, we can see that so it will be n over n1 factorial times n minus 1 factorial, n minus 1 factorial, n minus over n minus 1 factorial times n2 factorial. And so on. And we see here that something is cancelled. So and what left is just n factorial divided by n1 factorial, n2 factorial, and 3 factorial, and the last one will be nk factorial. So he will have nk factorial divided by n minus nk factorial times nk factorial, and this will be cancelled because this is just 0. And here, so it will be, so I need to rewrite this as, it is the same as n minus 1, etc. And this will be cancelled with the previous one. Okay, so we just proved that we have this formula for the polynomial coefficients. And of course, we have the polynomial theorem. It's the generation of the binomial theorem. So if we have, so in binomial theorem, we have only 2 parameters in the nth power, and here we'll have n variables. So if we take x1, etc., so I just need to take, it's better to take xk. So I take x1, x2, etc., xk as the variables, and I want to calculate the nth power of this sum. And if I open the brackets, I will have the sum from the g1 0 to n g. So I need, maybe it is better to write this as the tuple. So so the sum of this so sum of the coefficients is equal to n, and they are all from 0 to n. And here we have x1 in the j1 power, x2 in the j2 power, etc., xk in the jk power. And the coefficient in this term, in this monom, will be just polynomial coefficients of g1, g2, etc., jk. This is called the polynomial theorem or polynomial formula. So first remark, of course, if we take n equal to 2, then it will be just the binomial theorem. So if I just write this as, so I need to write the polynomial coefficient of g1, g2, x1 in the power g1, x2 in the power g2. So the sum of this is n, so I can write this as k n minus k, and here I'll have p k n minus k, and of course p n minus k is equal to n so kk n minus k, sorry. So it will be k n factorial divided by k factorial n minus k factorial is just the c and k. So it is just the binomial theorem. So we of course have generation of the theorem onto k terms, not just two terms. Okay, and the proof of this theorem is just similar to the proof of the binomial theorem, because what we so we need to like look at the product of the n such brackets. So we have x1 plus etc plus xk times x1 plus etc plus xk, and so this happens like n times. We have n brackets, and we want to calculate how can we choose the, so from each bracket we take one variable, and we want to calculate how many possible ways to choose the elements from the brackets where we have exactly j1 elements from the x1, j2 elements of the x2, and so on, jk elements from xk, and this is just the definition of the polynomial coefficient, because I take, so first I choose the brackets where we can take x1. So I just took, I have the g1 brackets where from which I take x1. Then I choose, so I have some brackets where I have g2 brackets where I can take the x2 variable, g3 brackets where I have x3, and so on. So the possible ways of choosing the elements from brackets such that it will be this monom, it will just exactly the polynomial coefficients by definition. And so if I take the summand of these coefficients, it will be the left-hand side. Do you have any questions? Or do you understand the proof, or maybe I need to be more precisely?
I think it's okay, sir.
Okay, good. Okay, so of course we have some exercises, but I think I will give 2 or 3 exercises more, and we will be finished for today. So for example, okay, so maybe just wait a minute. I just try to find any, and I will write them. Okay, so for example, so this will be the example. So for example, we need to find the following sum. If it seems hard, so maybe you can just try to calculate just the sum of the polynomial coefficients. So for example, we have the same task, but we want to find just the sum of the polynomial coefficients.
So is this a task? Like an exercise? Is this an exercise?
Yeah. It's just an example of using the polynomial theorem. You just look at this as try to look at the polynomial theorem just to find the answer. Yeah. So.
Sir, could you just do this first one for us? Then maybe the second one we'll try it.
Sorry, do you want a hint?
I said maybe you should do the first one with us, then maybe the second one we'll try
Okay.
it.
I will take the second one, and the first one will be in the home task. Okay. So
Okay.
it's because it is simpler. So if you want to, we already in the start of this lecture, I remind you that if you want to calculate the sum of the binomial coefficients, you just can use the binomial theorem. And here's the same idea. So if you want to calculate the sum of the polynomial coefficients, we just use the polynomial theorem. So here we could just write it as 1 plus 1 plus 1 in the power of n1 plus 1 plus n2 plus n3, because this is, if you look at the polynomial theorem, then it will give us the answer, because here we have variables in the different powers, but if we take x1, x2, and x3 is equal to 1, then this will be part is equal to 1, and so we just have the sum of the polynomial coefficients. And so this is just this guys will be the sum of the ones. So it will be just 3 in the fifth power. Okay?
Okay, so but when you say sum of the polynomials of n1, n2, n3,
Yeah.
starting from where to where?
Yeah, we just calculate the for all triples of n1, n2, n3 such that sum of them is equal to 5, and such as the natural numbers, so they differ from 0 to 5. We have natural numbers with 0, and it is just the same as the polynomial theorem. So in polynomial theorem, you have summoned only different parameters. So you have summoned over. So if you fix all the parameters except once, for example, we can rewrite the summand as the summand over g1, g2, etc. jk minus 1, and gk will be the last one. It will determine, so it will be n minus j1 minus j2 and so on. So like in the polynomial theorem, we have only one parameter left, so we summoned over one parameter. And so here we have summoned over k minus 1 parameters. Or we can just look at this as a summoned of all such tuples that some of them are equal to n. Yeah? Do you understand?
Not really, sir. The question I'm asking is that, for example, in the polynomial theorem, it's from j equals to 0 to n.
Yeah, but we sums over all tuples. So we just calculate this so we here we again we can write this as a summand over g1 from 1 to n, g2 from 1 to n minus g2, g1, g3 from 0 to n minus g1 minus g2, and something like that. It is the same as this one. Okay?
Okay, sir.
So
okay.
we can write, so we can like look at this as just summand of a subset. So we just look at those tuples. We look at all the tuples j1, j2, etc., jk, such that they are all non-negative integers, and the sum of them is equal to n. And then for each such tuple, we have the summand of p of j1, j2, etc., jk times x1 and the j1 power, x2 and the j2 power, and so on. Or we can derive the summand as combinations of the summands, but it is, I think it is just much complexified. So it's just complex way to write this sum. Yeah, okay?
Okay, sir.
Okay. So I think you can find the second sum using the idea for the first. Okay, so maybe more. So suppose it was, for example, I don't know, first exercise, second. Okay, so suppose we have 16 students and we want to divide them into 3 groups of 4 students and 2 groups of two students. So we have 2 possible variations. So the groups are distinct, so labeled by A, B, C, D, E, or groups of the same number of students are indistinct. So I need to write this like indistinct. Maybe it is better write just indistinguishable, but I think indistinguishable. Students. Oh, if it is very hard, we can start with 12 students and 3 groups of 4 students, if it is better. And then we can go to the more complicated situation. So we can ask the same questions for, just we have 12 students. We want to divide them into 3 groups of 4 students. And how many possible ways of doing that if groups are distinct? So if we have A, B, C, group A, group B, and group C, and if they are indistinguishable.
Sir, so how are we meant to present the answer?
You can describe it just at polynomial coefficients or just factorials. maybe.
Oh,
You can so if you have this as home task, I think you can use the calculator. It finds exactly the answer. But if you right now you just can give me the answer just as the factorials and the.
sir, can I give you the answers as a combinatoric in the combinatorial
Yeah.
form?
Okay. So what is the answer?
So for A, I think it's 16 choose 12 times 12 choose 4 times 8 choose 4 times 4 choose 2.
Okay. So so you can I write this as just as the P of 4, 4, 4, 2, 2, yes?
Could you explain why, sir?
First of all, we just prove when we prove the polynomial theorem, the form for polynomial coefficient, we have the same answer. So you have here you have you choose 4 from 16, then you choose 4 from 12, then you choose 4 from 8, then you choose 2 from 4. It is the same idea here, and the logic is the same, is the following. So we have 5 groups. It's just the definition of polynomial coefficient because we have 5 groups. Each group contains the exactly so the fixed number of students. So we have 4 students of type 1, 4 students of type 2, 4 students of type 3, 2 students of type 4, and 2 students of type 5. So we have exactly we have the amount of the different types of kind of students. So this is just the polynomial coefficient. This is just the definition, and
Okay.
so we have like this formula. So again, you give the correct answer, but we already explained it by each. So we just can give the explicit formula for this. Okay. What about?
Sir, you call this the polynomial coefficients?
Yes. This is just a polynomial coefficient. Polynomial coefficient. Similar to the binomial coefficient. So binomial coefficient is a coefficient in the binomial theorem. And the polynomial coefficient is what occurs in the polynomial theorem. So it's just the generation. In binomial coefficient, it's just you have the 2 of them. So we will have 2 groups. You just write that will be just the combinations of n over k. So this is just the generation of this concept is polynomial coefficient.
Sir, so maybe the next one is P 12,4.
Sorry, P
12,4.
Yeah, but the groups are indistinguishable. It doesn't mean that we can combine them. So
Okay.
it means that we just need to. So suppose we just have 16 students in the one classroom, and we want to divide it by groups, but they are not labeled because we have just groups of 4 people, groups of 4 people, groups of 4 people, groups of 2, and groups of 2 people, and we cannot change the 2 groups of the 4. We change the places of the 2 groups of the 4. It will be the same partition as previous. So we can change the groups of the same number of people, and the partition will be the same.
Sir, so is it P of 3, 2?
So you you think that will be so just the 5 factorial over 3 factorial times 2 factorial, so just like 10 something.
Am I right?
You have the right idea. So you just, so if you look at the P 3,2, it's just the possible combinations of these groups. So we have five groups, and you want to calculate how the number of possible combinations of these groups do we have. Of course, we have the 10 possible combinations, but you don't want to forget that there are 16 students, and we want to divide them into these groups. So if you want to give the correct answer, you just need to calculate. So you need to calculate the product of this guys. So again, so we have 16 factorial possible permutations of these people. Then we divide them by the possible groups. So maybe this is not entirely correct, but we start with this one, and then we have the 3 groups of the 4 people and 2 groups of 2 people, and we can change them. We can change the places of them. So if you want to forget about the combinations of 2 possible groups, we just need to divide over 2 factorial, because for each possible combination we have, so for each possible groups, we have groups D and E, and we have the same combination of group E and D. So we can change the places of them. So we have 16 people. So for example, if we choose these guys as 2 group and these guys as 2 group, and we can choose also these guys as 2 group and these guys as 2 group, and this is the same. So we calculate these combinations 2 times, and for groups of 4 people, we have the 1 over 3 factorial kind of permutation. So for example, we have these guys. No, this is green. Red ones and blue ones. So we can choose these ones, or these ones, or these ones, or these ones, or these ones. So, do you understand the idea? No?
Sir, please, could you explain to us when you say something is indistinguishable and it's distinguishable?
So, if I talk about if all groups are distinct, we just have the 5 groups, 3 groups bigger of the 4 people and two groups smaller of the 2 people. Yeah.
Yes,
and
sir.
so if they are all distinguishable, so we have the group A, group B, group C, group D, and group E. We just can take the people from group A, then from group B, then from group C, and so on. So it's just the polynomial coefficients. But if we forget about the letters of this, so if the groups are indistinguishable, so these three groups are indistinguishable, and these 2 are indistinguishable. It means that we can permutate them. So we can fix the groups and permutate the groups, and we will have the same distribution of the students. Okay. So for example, if we have this group A, this group B, this group C, and we have choose this group A, this group B, this group A, this group C, it will be the same distribution of the students. but we have exactly 6 types, so 3 factorial types of permutations of these 3 groups. So, and 2 factorials here. So we just need to divide this over 3 factorial and over 2 factorial, just to calculate the number of possible variations. Okay?
Yes, sir. Yes, sir.
Okay. Okay. Okay, so I think this is enough for today. So if you have any questions, you can ask, and otherwise, so I think I will make a homework. Again, it will be just for 2 weeks. And maybe I don't make it today, but maybe until the end of the weekend, I will have and put it in the Telegram group. Okay?
Okay, sir.
Okay. So,
and sir, if we submit our homework before the deadline,
yes.
but we make a mistake, can we submit it again?
Yeah, but
if it's comfortable for you.
Yeah, but if you send it just in 1 hour before the deadline, I will have not much time to check it. So,
of course, sir.
Yeah. So if you have just 1 day or 2 days, I will try to look through it and try to find the mistakes.
Okay.
Okay.
Yes, sir.
Yeah.
Okay. Thank you, sir.
Yeah. Thank you.
Goodbye,
Bye.
sir.
Bye.